I'm fine.
Pop quiz.
Do you like with pop quizzes and you give us like one of those like soda pops and like popcorn? Like, you know, like the primary does for Father's Day. Oh yeah, I think all that stuff should come in pop quiz.
Okay. So this is something for you. However, it's not a quiz.
Is it a trick for it?
It's a test.
The front page looks like a test.
Front page does look like a test, doesn't it? Okay.
It's a test.
It's. Did we have a review tape the previous time?
No, but
Then
like,
it's not a test.
well, you would do that.
No, I wouldn't. I'm not that mean. Okay. This is, however, to hopefully help you get ready for the test. Okay.
It is a test.
So what I've done, this is the same information that you get on the test. Okay, this is the same thing. Okay.
Wait, the whole thing.
This is the front page. You always will get this front page.
Oh, this is the front page?
No,
Okay.
he's giving us the entire headset.
And there are a number of calculations. Okay. And I'm going to give you some time to work on these. And if you can do these calculations, you're ready for the test. If you can't do these, okay, if you can't do these, that's going to tell you where you want to spend a little bit of time studying. Okay. So I'm going to hand these out, and I'll give you some time, probably like, I don't know, 30, 35 minutes or so. We'll see where you are at that point. There's only 7 things. There's only 7 things, and some of them you should be able to do very quickly. I would also say, if you're stuck on one, move to a new one. Okay. This isn't a test. This is to help you figure out what you know and what you don't know. We'll go over it in a little while. But yes, so we do have the test coming up next week. Like I said, if you can do these calculations, you should be able to do the calculations on the test. If you can't do these calculations, then
Are you serious? Get out of here. Get out. We're in a school. You really think this is the only place that a pencil has?
Sorry, my bad, Mr. Roy.
Get out. I don't even know.
If you can't do the calculations, that means you need to work on that before the test. So obviously you can use a calculator for this. Also, for this, I don't mind if you use your book to look stuff up. Obviously you can't do that on the test. So it'd be better if you can do this without using your book. But anyway, for anyone who's watching this on YouTube instead of here in class, I will post this on LMS, and we'll go from there. I'll pause the recording so that you don't have to sit and watch a blank screen for 30 minutes. But yeah, so let's go ahead and get started with this. Like I said, use a calculator, see what you know, see where you're struggling.
Wait.
All right, so let's talk about this a little bit. Hopefully the problems at least seem somewhat familiar. Anyway, so let's just start at the beginning. We'll see how much we can get through before the end of class. So the first one deals with pressure. The pressure in a tire is 1.88 atmosphere at 25 degrees Celsius. What will the pressure be if the temperature increases to 37 degrees Celsius? Okay. So if we look on the front here, right there. Right there is our combined gas law. Okay. Now, the problem gave us pressure and temperature. Didn't give us anything about volume. If the problem doesn't give you anything about volume, we assume that it's constant, and we take it out of our combined gas law. Okay. Remember, we had the 3 different gas laws. Okay. Charles's law, Davis-Sachs, and there's one more. The name is escaping me now, but anyway. But they all come together to form the combined, which is what's on here. So, pressure 1, 1.88 atmosphere. Temperature 1, 25 degrees Celsius. Pressure 2, that's what we want to find out. Temperature 2, 37 degrees Celsius. Okay. I haven't done these personally yet, so let's pull out my calculator. Remember, temperature. When we're dealing with gas laws, temperature has to be converted to Kelvin. Okay, so how do we do that? 273. 273, very good. We take 25, we add 273. This one, do the same thing. We get that. Okay, now we need to rearrange, do some algebra to get pressure 2 by itself. And that's going to end up looking like this. And now we just pull in everything. So we have 1.33 atmosphere, temperature 2, 310 Kelvin, temperature 1, 298 Kelvin. Kelvin offsets, they cancel out. We're left with atmosphere, which is what we want because it's pressure. We have 1.88 times 310. And we divide that by 298. And our new pressure is going to be 1.96. Okay. The next one. Balloon contains 146 milliliters of gas at a pressure of 1.30 atmosphere and a temperature of 5 degrees Celsius. The pressure doubles and the temperature decreases to 2.0 Celsius. What will the volume of the gas? What will be the volume of gas in the balloon? Once again, we're going to start with our combined gas law. This time we have all 3 of the values. Okay, we've got volume, we have pressure, we have temperature. So we're going to use the entire combined gas law. Let's start writing down what we know. Our first pressure, 1.30 atmosphere. Our first volume, 146 milliliters. Our first temperature, 5 degrees Celsius. All right, second condition, pressure. It doesn't give us an exact number, but it says it doubles. Okay, so we just take that, multiply by 2. Alternatively, the math would work out the same if we put that as 1 and that as 2. But if you don't want to deal with that, just take that and multiply by 2. B2, that's what we're trying to find out. And T2, 2 degrees Celsius. So convert these to Kelvin. Okay. We want to solve for B2, which is going to end up looking like this. Once again, if you can't do it in your head that fast, that's not a problem. Just do the steps, work it out. Okay. And once we have solved for B2, we can start pulling things in. Okay. So 1.0 atmosphere times our initial volume, and 46 milliliters times temperature here, but this is temperature 2. Temperature 1 times our initial pressure. Oh, 2. Oh, yeah. There's 2 right there. I don't know why I put a 1 right there. Okay. Then okay. Now we go to our calculator. 1.3 times 246 times 275. Divide that by 278 times 2.6, and it's going to give us 72.2. Okay. The next one is a gas stoichiometry problem. So it gives us this reaction. And it wants to know the volume of oxygen gas at STP required to completely react with 52 grams of iron. Okay. So we'll start with 52 grams of iron. It's already balanced. That would be our first step. If it wasn't, always double check to see if it's balanced. You should know by now that I will give you a problem without a balanced equation sometimes. Sometimes I give it to you balanced, sometimes I don't. So just double check, make sure that it's balanced. So we want to change this to moles. So we look at our periodic table and we see that we have 55.8, we'll round it off 85 grams in 1 mole. Okay, so now we're in moles of iron. Now is where we can do our stoichiometric ratio. We know that 4 moles of iron will react with 3 moles of oxygen. And that's actually where we want to stop with that calculation. So we do that. And what we're going to be left with is 0.698 moles of oxygen. But now, we go to our ideal gas law. Okay. And pressure. It doesn't give us the exact numeric pressure, but it tells us we're at STP, which means that's 1 atmosphere. Volume, that's what it's asking for. The number of moles, that's what we calculated. R. Remember, that's a constant. We find it on the front of the sheet. Okay. Gives us 2 different values for R right there, depending on which units we're in. STP is in atmosphere, so we're going to use the value of R that's in atmosphere. And then temperature, once again, that comes from STP, 273 Kelvin, 0 degrees Celsius. Okay. Do our algebra. And fill in what we have. All divided by 1 atmosphere. That makes it easy. Dividing by 1 makes things easy. So that goes away, that goes away, that goes away. We're just left with liters, which is exactly what we want. And we do the math. And that gives us 15 point, we'll call it 6.5. Okay, this next one. How many milliliters of a 5 molar sulfuric acid stock solution would you need to prepare 100 milliliters of a, looks like there's a typo, should be of a solution, or get rid of that A, but that doesn't matter. Still makes sense. Okay, so this is this dilution equation right there. M1V1 equals M2V2. Okay. So M is molarity. Our original molarity, 5.0. The volume of that is what we're trying to find. The molarity we're trying to get to, 0.25. And the volume that we need is 0.1 liters, 100 milliliters. Okay. Although I guess it asks 4 milliliters, so we'll just do it in milliliters. Although no, because that's moles per liter, so although it's going to cancel out, so it'll be fine. So solve for V1. Okay, so we have 0.25 times 100 milliliters. Right there. Divided by, okay. And now we just need our calculator. We need 5. Let's see, we're running low on time, so let's see how fast we can get through some of these. Okay, The mass of sodium hydroxide in 250 milliliters of a 3 molar sodium hydroxide solution. Okay. So we're going to start with 250 milliliters. And what we need to remember is that in a 3 molar solution, okay, we have 3 moles in 1 liter. Now we do need to get rid of that milliliters. So 1,000 milliliters in 1 liter. So that's going to tell us how many moles there are in what we have. And then to get the mass, once again.
So is it 1 liter equal to 3 moles?
Yes, so if it's 3 molar, the 3 with the big M, that means in every liter of solution, there are 3 moles of whatever you have.
Okay.
And then to get the mass, go to our periodic table, take sodium, 9 plus 1 oxygen, plus hydrogen. We're going to call that 1 mole, 39.996 grams. And then you multiply across the top, 350, and we divide by everything in the bottom, 1,000. And that's going to tell us we have 29.997. And I am doing this fast, so if I hit a key wrong, possible. But anyway. Equilibrium expressions. This is what we've just been doing, so hopefully these ones weren't too bad. But that first one is homogeneous, so we need all of them. Okay. So our K expression, we have our methane, we have our water, we have our carbon monoxide, and our hydrogen we raise to the 3rd power because it has a 3 when it's balanced. For this other one, the second one, it is heterogeneous. So if we write everything out first, and then get rid of our solids. We're just left with CO2. All right, got like 2 minutes left for this last one. So this is, will a precipitate form? So we have equal volumes, which is nice because that means for our initial concentrations, we just cut them in half. Okay, so we're going to have for our lead ion concentration, this is that, and for our fluorine ion, again, we're going to cut that in half. We got that. So our equation tells us that we're dealing with this. So that's going to break apart like this. So our we'll just start with Q. Our QSP. The arrow is not equal sign. QSP equal to the lead times the fluorine squared. Remember, QSP is set up just like KSP. We put these numbers in. Then we go to our calculator. 5, 0.015 squared. That is 1.125 times 10 to the minus fifth. And that gives us our KSP at 3.3 times 10 to the minus 8. QSP is bigger, so we will get a percent. Okay, like I said, if you can do those, you'll be good for the test. If some of those you were struggling with, take some time, do some practice. Watch this again on YouTube. So, all right, see you guys next time.